Welcome, ladies and gentlemen. Welcome for the online technical seminar on lightning protection. Today we are going to discuss about safeguarding buildings and equipment. The webinar is organized by Zambian Center for Lightning Research and jointly by the Center for Excellence on High Voltage Engineering, University Witwatersrand, South Africa. So you know very well that we were regularly organizing webinars on behalf of various organizations, especially with respect to SALNet. So today we have three programs. Three people are mainly going to talk about the activities. First, I would like to invite Ms. Foster Lubasi, the founder of Zaclayer, for a small explanation about the activities which they are doing in the region. Followed by, we will have a small presentation by Mr. Alexis about the lightning protection of structures. Then after that, we have a small session about surge protection devices for low voltage system by Dr. Chandima. So my name is Gopakumar. For the convenience, I switch off my camera. Otherwise, sometime it creates some disturbance in the signal. Uh, Miss Foster, she is the founder and the director of the Zambian Center for Lightning and an active member in lightning awareness programs in Africa. She was also there last year in India in our SALNet, the meeting which was organized in India. So I would like to, I welcome Ms. Foster to have the presentation on the fundamental characteristics of lightning. Over to you, Ms. Foster.
Good day, everyone. Before I do a short presentation on the fundamental characteristics of lightning, I've been asked to say something briefly about the Zambian Center for Lightning Information and Research, Zaclayer. Zaclayer is an offshoot of the African Centers for Lightning and Electromagnetics, ARCONET. The idea of ARCONET was birthed in Kathmandu, Nepal, at an international symposium on lightning protection organized by Dr. Sharma and his team. At the conference, Professor Gomes called a side meeting with all the scientists participants from Africa. In that meeting, we agreed that the African countries needed to work together and that we needed to organize an African conference on lightning protection to discuss or chart a way forward. Consequently, we had two conferences in Uganda organized by Mr. Richard Tushemerere and his team. The first meeting took place in February 2013 in Kampala, and the second took place in March 2014 in Entebbe. The key outcome for both the conferences was the agreement that each African country needed to set up a center for lightning research to spearhead the lightning protection and safety in our countries, as we did recognize that lightning was a hazard in Africa, and yet it wasn't getting the required attention. So we did discuss that we needed to bring to the attention of authorities in our countries in Africa so that this issue can be addressed. That is how come in 2014 November, an office for Zambian Center for Lightning Information and Research was established at ZASTI, at Zambia Air Services Training Institute, as a result of hard work by me and two other colleagues, namely Mr. Silumelume Nyambe and Mr. Lyford Makwetula, both senior lecturers at ZASTI. Mr. Makwetula has since passed on because of high blood pressure. We were later joined by Mr. Alik Malichi, a senior lecturer at the University of Zambia, who has also since passed on in a car accident. In that sense, we can say Zakir hasn't been so lucky. Zakir was inaugurated in 2015 August at the International Conference on Lightning Protection it hosted in Lusaka, Zambia, by Her Excellency the Vice President of the Republic of Zambia, Her Honorable Inongawina, who was represented by Honorable Lazarus Chungu, Deputy Minister in the Office of the Vice President. Since then, Zakir, in conjunction with the University of Zambia and the World Academy of Sciences, hosted Professor Gomes as visiting professor for 2 weeks. Needful to mention that Mr. Alec Malichi was very instrumental in the successful accomplishment of the visiting professor program, which resulted in Professor Gomes helping the University of Zambia establish master's programs in high voltage and electromagnetic compatibility and security concerns. The programs are enrolling right now as I speak and should start running in January 2021. I have also actually enrolled for the EMC program, the electromagnetic compatibility program. The visiting professor also visited key institutions such as ZESCO, ZICTA, Zambia Airports Corporation, ZASTI, Zambia National Broadcasting Corporation, and Copperbelt Energy. These visits have strengthened the cooperation between these institutions and Zakir on matters of lightning protection and basic electrical safety. Zakir has had 2 meetings with Lusaka City Council and other stakeholders to bring to the fore the need for reinforcing the law on lightning protection for houses and other buildings in the country. We've had several meetings with the various representatives from the Ministry of Chiefs and Traditional Affairs through the House of Chiefs concerning lightning protection and lightning awareness campaigns in rural areas. We hope that after the COVID situation has been brought under control, Ter, a student under Professor Price at Tel Aviv University, with other students, can visit Zambia and help with the awareness campaigns. Because we were in the process of those discussions when the COVID situation came into place. So I hope Ter has continued to organize our fellow students that as soon as the situation for COVID is brought under control, we can resume the discussions and hopefully the students from Israel, Tel Aviv University can visit Zambia and help us with the awareness campaigns in the rural areas. That's how far we've come. And I would really like to thank NAM S&T, Professor Arun, for all the support, advice, and sponsorship of the conferences. And I would love to thank Professor Gomes for all the effort and sacrifices he's made to help Zakir come this far. May I also say UNZA is looking to you, sir, for help to ensure the high voltage and EMC programs succeed. I saw a request for training materials from one of the lecturers from the University of Zambia on the registration list in the comments section. I hope you take time to read through the comment section in the registration list. I'm sure there are more requests to you, sir, especially concerning the high voltage and EMC programs at the University of Zambia.
Like I said, this is really just the fundamentals. I mean, it was really meant to just remind us all about the fundamental basics of lightning. Sorry, I had that problem, but this is how the presentation goes. Myths about lightning. like we all know, every place and every people have myths or had myths, but some still have myths on lightning. We get the Scandinavia with the god of lightning, Greece there with the god that sends lightning. We can go on and on. I just want to say a bit about Zambia. In Zambia, it is believed that if lightning strikes a place or a person, there must be something evil going on. Someone has sent lightning either for vengeance or to just punish. People struck are perceived to be evil, and God is punishing them. I mean, lightning for many people out here remains a mystery and terribly feared. Like you can see here, we had a house destroyed. That was in 2012. 5 people dead from the same family, 1 alive, and people don't even want to get near to a place that has been struck by lightning. This block you're seeing here is a classroom and some offices. I was struck by lightning and been totally abandoned. Actually, when we went to do research, we had to drag the people you're seeing in the picture to the building because they didn't want to come with us. But we promised them that if anything happens to them, we'll be responsible. Okay, we get to lightning. Just reminding ourselves that lightning originates from the clouds, and in particular the cumulonimbus. The meteorologists will help us. Clouds, which are highly associated with thunderstorms and heavy precipitation. We see that these clouds are about 1 to 2 kilometers above the ground, and that's the base. The top will go as far as 15 kilometers above the ground. The lightning formation in the clouds is, we are told, is as a result of the collision between the ice particles and the water vapor particles. Although how the charge separates, this charge separation mechanism in the clouds is not fully understood, scientists do tell us from their studies that the studies have shown that ice crystals tend to stay at the top of the cloud. So we presume they're lighter and they develop a positive charge, while the heavy mixture of water and ice called the groupel moves towards the bottom of the clouds and develops a negative charge. And although the cumulonimbus cloud starts about 1 to 2 kilometers above the ground, we notice that the formation of lightning can only start about 4 to 5 kilometers when it crosses the 0 degrees Celsius freezing point isotherm. Yeah, so it looks something like that. We have the ice crystals on top there, where you have the positive, and then about 4 to 5 kilometers above the ground, we have the negative charge. That means that's where the water and the ice, the mixture of water and ice are, and therefore the negative charge. We know the 3 types of lightning that we know about is that there is inside the cloud lightning, which is called intra-cloud lightning. The same in the one cloud, and then the lighting, there's some discharges in the same cloud. But we also have discharges between clouds, that's cloud to cloud, or intercloud lightning, and then between the cloud and the ground, which is the lightning that we see coming from the sky, from the cloud to the ground. And of course, that's the one we deal with because that's the one we interact with. But I said, unfortunately, not in a friendly manner. So let's say something about the cloud formation here. We concentrate on the sun hitting the surface of the earth and the air parcels drifting up. And we also know about another way that the air can lift up, that is called the horizontal, that is the air being forced up by the horizontal pressure gradient forces. But I think the one we mainly used with is about the heat cycle that hits the air, and the air goes up, and you can see it condenses. when the air becomes super saturated, when it gets to about 1 to 2 kilometers above the ground, you see the clouds beginning to form. Yeah. And of course, the air and the water mixtures continue to rise. And as it crosses the 0 degrees isotherm, it begins to freeze. So you have water, ice mixture. And as it goes further up, the higher you go, the cooler it becomes. So the ice forms at the top at about 15 kilometers above the ground. And of course, like we said, how the charge separates is still a field of study, challenge to the students. I hope we have some students in the webinar who can take up some of these challenges, areas of research, because all the scientists tell us is they don't understand. We don't all understand how the charge separation takes place. However, it's been from the studies, it's been known that the ice crystals that settle at the top of the cumulonimbus cloud develop a positive charge, and the heavy mixture of water and ice, the group at the bottom of the cloud, though not exactly at the bottom, we're talking about 4 to 5 kilometers above the ground, develop a positive charge. But then we also know that the cloud also moves horizontally. And as the cloud moves, the thundercloud moves, we know from science that an echo, as it's going, an equal and opposite charge is induced in the surface of the Earth in its path. And the induced voltage at any point will increase as the cloud is approaching and reaches its maximum when the center of the cloud arrives. But then as the cloud passes, that voltage drops. And then we also know that as the cloud is moving, an electrically conductive channel of ionized air is initiated in the cloud. Again, that's another area of research, because just there are these charges, the negative and the positive charges in the cloud, but how this channel begins to form is still an area of study, because the mechanism by which this ionized air channel begins to form in the cloud is not yet known. However, it does form, and it's called a leader. And this channel begins to propagate itself downwards in a discontinuous manner, and that's why it's called a stepped leader. As it goes down, it actually goes in steps. It will go like 50 meters, and then it will stop, and then it will ionize the air at its leading tip. And when it ionizes, when the air around it is ionized, we see more leaders being formed, and it moves on. Therefore, it moves in a jerky manner. And this is why it's called the stepped leader, and it moves towards the Earth. We're told that as it gets closer to the Earth, actually, it gets faster for obvious reasons, because there's the other charge that has formed, the opposite charge that has formed on the Earth, and it's also attracting. There's a magnetic field between the stepped leader that's approaching from the cloud and the charges that are forming on the ground as it's moving. We told that the average speed of the stepped leader is in the order of 10 to the power of 5 meters per second. And I've already said the ionized channels between ion pools about 40 to 50 meters long. That's the leaders as they are going down towards the Earth. And these leaders are going towards the Earth. We recognize that the localized electric fields begin to get strengthened as the negative leaders approach the ground. And we recognize also that as the objects on the ground, begin to experience coronal discharge because of the electric fields around them. And as the lightning the step leader approaches, the objects that exceed the threshold and begin to form upward streamers. So in other words, they also begin to form channels going up to meet because they're breaking down the insulation between them, and because the electric field between them is getting stronger. So once a downward leader attaches to an upward streamer, a low resistance channel is completed, and a massive electric discharge called the return stroke follows. Now, this is the most luminous and noticeable part of the lightning, and most likely that's what most of us know as lightning. But before that, there was all this taking place. Yeah, it looks something like that. I'm sure we've all seen something like that in the skies from time to time. Yeah. So when that return stroke, we see that the core temperature during the return stroke may actually exceed 50,000 Kelvin. For us who are used to degrees Celsius, is about 49,726.85 degrees Celsius. The instantaneous heat during the return stroke, it heats up, so causes air to explosively expand, producing a powerful shock wave we hear as thunder. I know most of us, when we heard thunder, it was like, ooh, God is screaming or God is angry. But with science now, we know that actually it's just the quick or fast, very, very fast expansion of air. It's explosive and it causes thunder. And most negative cloud to ground flashes are usually not just one. You have, sometimes they can be 3 to 4 and can actually go up to 30. And that's why you find that one lightning can actually strike a number of places, and one lightning flash can strike a number of places and a number of people. And yeah, even I used to get shocked. One strike, so many people. And every strike is preceded by a dart leader. A dart leader is just like, in the first instance, it was a stepped leader, but the dart leaders are the ones that assist, that form channels for the restrike strokes. A dart leader, we know, is not stepped because the channel is already established in the first place by the step leader. Then an average duration of lightning is about 30 microseconds, and lightning can have multi-point termination, which we've already talked about, to the ground. And when it does that, it's called multi-point lightning or fork lightning, when it has too many termination points. So in all this, we do learn that a lightning flash is not just one act, and we get lightning. We see it's a combination of the step leader, which we talked about, the upward streamers, the return stroke, the dart leaders, and subsequent return strokes. So all those combined together, that is what we call a lightning flash. And the current in the lightning transient can rise to the peak within 1 to 10 microseconds, but decays within 50 to 200 microseconds. An average bolt of negative lightning carries an average electric current of about 30 kiloamps, transfers 15 coulombs of charge and 500 megajoules of energy. And this is what it can do. Here we had a power cable for our radiation monitors. I hope Radiation Protection Authority is logged in, because this is the equipment where the power supply cable was struck by lightning. We are also actually told that we know that a large boat can actually carry up to 120 kiloamps and 350 coulombs of charge. So you can actually calculate the energy from those that equation. And this, as you can see from the energy and the power of lightning, how it can, a huge tree like this struck and split into this kind of pieces. I think that's basically what that I had to share on this. So thank you so much.
Thank you very much, Mrs. Foster. It was a nice presentation. So,
thank you.
Okay. So, gentlemen, we are going ahead with the second presentation by Mr. Alexis. The subject is about lightning protection of structures. Mr. Alexis, you have about 40 minutes for the presentation. And Mr. Alexis, my job is to introduce him. He's an electrical and electronics engineer. He is the member or the chairman of the TC81 National Committee in South Africa. He is also actively involved in several lightning protection and educational activities. So I request Mr. Alexis, please come forward and have your presentation.
Thanks, Kopa. Appreciate that. Thank you, Ron. Good afternoon. As I said to Foster, we always love and enjoy to assist our fellow Africans to teach these skills about lightning protection, which we have gained from others, and we hope to pass on to not only the next generation, but also to our fellow Africans like Foster, who's doing amazing work in Central Africa. Today, I will be speaking about lightning protection for structures, and the approach that has been taken is one of how to incorporate natural elements, how to use what one has, and to understand that a lightning protection system does not necessarily have to mean it is an expensive system. And obviously, as you can imagine, in Africa, we have the huge socioeconomic differences to first world countries, so we have to be very cognizant of the costs associated with our design. Within the agenda, we will cover damages which we have seen to structures, so the different types of damages, so that one can understand if these certain damages are associated with structures, what would one need to do in order to mitigate those? We'd move on to the characteristics of lightning. Foster would have had a very interesting presentation on the science behind the characteristics. For us, it's important to understand, again, what happens when lightning strikes a certain object and what do we need to take care of. Finally, we will move on to what constitutes an entire lightning protection system. What is an external part? What is the internal part of the system?
Okay.
Finally, we will move on to testing and maintenance.
No,
And just mute that person. I've got that.
Yes, that's muted.
Thanks, Kopa. I also see I had the function. Moving on. Here we see different types of buildings that have been destroyed by lightning. We noticed that even some roofs that are made of thatch, as an example, or a dried grass reed is quite a common roof surface in Africa. We have electric and or telecommunication lines that get damaged, such as electrical distribution board. We have occupants or even animals, as part of a system which have been killed as a result of lightning. We also have different types of constructions. Some are using brick and mortar, others are using clay, and we see the different results as from lightning strikes to these different types of constructions. And then finally, the electronics, obviously causing, as we've seen in the introduction, or at least in the invitation of this session today, costing millions and millions of euros damages every year in Africa. What is important is that we notice and we see all these types of lightning damages. One now has to take an approach in order to ensure that we don't have structures being burned, structures being mechanically damaged, electrical failures, electronic damages, and even the occupants themselves to be safe. In order to do that, we will have to look at three main characteristics of lightning. I think it is quite common that most people understand that lightning is a current, so it's quite commonly seen that people at least take into consideration one of the characteristics, which is the peak value of the lightning current. However, very often we see that it is overlooked about the specific energy, so let's call it the heat that is injected into a system as a result of the lightning current. And then the third point is the mechanical force which lightning exerts. So once it strikes a certain object, we've seen trees splinter. Professor Gomez has done some very interesting papers on that. We've seen structures really being ripped apart. And so we realize that not only are we dealing with a current, we're dealing with quite a intense heat, a specific energy, and as a result of that, we're also dealing with a unique and extremely strong mechanical force. And we have to design systems knowing and understanding these characteristics of lightning. Let's understand first and foremost what is a lightning protection system, and we use now the IEC standards which Gopa referred to earlier, and we see that the purpose of an LPS, the acronym for Lightning Protection Systems, is a complete system, right? Used to protect the building, used to reduce or restrict the physical damage to that structure, but more importantly also to have a lightning safety factor for the occupants. And so it's both of these things. So it's a purposefully built system that offers both protection to the building as well as the occupants. A lightning protection system consists of both an external, so the outer, if you think about it, something outside, something that is exposed to weather conditions, as well as an internal, something that would be inside the building. And this is where we first understand that there is a split between the external part of a lightning protection system and also that there is an internal part to a lightning protection system. If we take a deep dive into external lightning protection, so the outer parts, let's understand the purpose or the function at least of the system. The first and foremost part is the interception. I have said this in a previous presentation that I love the German word for this part. They speak of a Fangspitze, which is basically translating to a catching rod. And really that's the part, the first part is the air termination system is there to intercept or in bad English to catch the lightning. And then once we've intercepted that lightning strike, we have to find a way to safely and controllably, two very important words, to conduct this intercepted lightning down to the earthing system or to the earth itself. And this is done via the down conductor system. Finally, once the currents have now been intercepted and controlled all the way down to earth, we need to find a means how we dissipate these currents into what is better known as an earth electrode or an earthing system. The terminology used in the standard refers to an earth termination system. And we have to do this whilst minimizing potentially dangerous conditions. And so it refers back to, we see the word safe and controlled, we see the words potentially dangerous conditions. We remember again that a lightning protection system is there to protect the building as well as the occupants to create safe and effective ways of dealing with the strike. The function of an internal lightning protection system is a very simple explanation, or at least a very simple expression, but quite a complex thing to achieve at times. And so I'm really excited to share this with you and also Professor Gomez will get into one of the critical parts, the surge protection measures. But in a very simple terms, the function of an internal system is to avoid any flashovers, sparking, or arcing. And we do this by two methods, either by keeping a separated distance or by keeping a distance away such that a sparking cannot happen. Or we all have learned and know the word bonding. So there is the term in the standard speaks of lightning equipotential bonding between any metal parts. And lightning equipotential bonding will be explained a little bit later, but in essence says we are trying to equalize any potential differences by a bonding method, either direct or indirect. Because if we equalize the potentials between two parts, we know that this mitigates any currents to flow, any arcing to happen, sparking and or damages. So here is a typical example of a school building. I chose to use a school building because along with ACLE Net and Foster, as she's referenced them, we have been dealing with quite a number of schools in and around countries like Congo and Uganda and Zambia as well. So here's a typical school. Might have solar, might not. We see some air termination system marked with red. So those are the catchers, the interceptors. We see the blue is the down conductor system. So conducting it safely down to earth itself. Here we can see that the columns, the natural elements that are already present in the building is being used. And then finally, we see an earthing system or the earth termination system in green. And we also have the lightning equipotential bonding happening then obviously from here on towards the internal side. So here we see already the key elements to a lightning protection system, at least the external part. I state here that in order to design a safe and effective system, a lightning protection designer not only has to take into consideration the requirements of the standards, right? We know that. But it's also got to be cognizant of the associated costs. So it means nothing to build this massive, very over-the-top type of system, just such that the costs are high but not effective for the protection itself. Dopa, we have a hand raised. I don't know how you want to deal with hands raised.
Yes, there is one person, but Mr. Alexis, are you using one more screen nearby? Because we are getting an echo from your sound.
So not from my side. It's ever since this person, okay. Dr. Lemba, has unmuted himself.
Okay. Dr. Lemba, you have any questions? I think no. So the hand is...
So again, just stating that, especially for Africa, we've got to be cognizant of the cost and weigh up the benefits of the system. It's important that the designer finds ways to be safe, practical, and cost effective. And this is really where one starts understanding how to incorporate natural materials or even materials which are in country, as opposed to materials we as designers might be used to using within our designs. Taking a look at the air termination system. So as I said earlier, the Germans almost call it the catching system. The purpose of it is to intercept. We know that now, right? That's quite, well, that's been explained. However, what's very important is that the lightning protection designers should consider the placement of these terminals very carefully, because this is the strategic position that we've got to find such that we will intercept the direct strike to the building. The standards give us methods how we can do this, but again, being practical about it, as we said, we've got to give a bit of a more pragmatic answer than only saying, well, use these methods, because sometimes these methods are, software driven, or it is quite complex calculations. And as many Africans in developing countries don't have those tools necessarily at hand. So we look at some of the practical points. Here we see that the standard guides us to say these catching systems or these air terminals should be placed on corners. Any exposed points, so sharp edges like a facade or a pitched part of a roof, right? And this is a great concept to say, let's start by placing air terminals on these exposed points, corners, on edges. Select a certain height of the air terminal and then apply some simplified mathematical models, such as the rolling sphere method, which is derived from the standard, as well as perhaps even combining the rolling sphere method with a protective angle method to make a more practical, cost-effective example. And let me show you what I mean. In the IEC standard, we see that for certain levels of protection, 1 to 4, we have a bandwidth of lightning currents which we can then intercept. So basically we are fail-proofing the system. So for a lightning protection level 1, any lightning current above 3000 amps will be captured or will be caught by the system. The lightning protection level 4, as an example, will start only from about 16 Ka. And this is where I've had great and very insightful chats with the Vaisala group, where we start seeing data coming back from African countries as to the average minimum peak values, because this will determine our protection levels. But let's carry on, and I showed to you what we are stating by this. If you see on the right, we have this building now, and the rolling sphere method basically says we have a sized sphere. So here you can see the sizes. The radius of the sphere is 20 meters for level 1 and 60 meters for level 4. So we would take this sphere, so a big round ball, make it as large as the lightning level would request us to, and then we have to roll this ball over the building. As you can see here on the top, so we first roll it from west to east, and then maybe from north to south. And wherever the ball has touched the surface of this structure or building, those are then identified as points where lightning could possibly attach. So that's where lightning would strike or could strike. By knowing this, we have obviously identified, as you can see by the illustration, red or dangerous areas where we need to place our catchers in strategic positions. However, looking at this on the right and knowing that we need software, we need 3D, we need trained technicians, it's almost, just a step too far, and we need to take a little bit more practical approach. So let me show you what we've done. In the 3D scenario, as I said, with the software, this is what happens. We're rolling a ball over, in every direction, all across this building, and we highlight the areas where lightning can possibly intercept. And by knowing this, as I stated earlier, we identify where we need to place our air termination system or the catching system, right? Now the problem is, as stated, this is all software driven, might not be able to have these type of tools. So what we have said is the following. Take the corners. So we have these, you see the 1 meter finials on the corners, right? Because the standard guided us. Take the corners, exposed edges and points, and place a certain height, pick a height, 1 meter, 2 meters, and then use the sag concept. So the sag concept is if you take the rolling sphere between, example, this point here and that point there on the right of the building, if you had the rolling sphere in between these, the sag is the depth of that sphere itself from the top point to the bottom. So here we can see, as an example, if the height of the air terminals is example 4 meters, and we are dealing with lightning level 1, that the sag will be 0.1 meters. What that means is we have to select our terminals such that the sag is less than the actual terminal's height to ensure that we're not exposing the building. We are in fact ensuring that we are striking the terminals. So we are in a more practical manner applying the rolling sphere method by saying, okay, if the terminals are X meters apart, we know what the sag is. And so if the sag is, example here, 0.1 meters, we should make our terminals, our catching rods, a little bit higher than 0.1 meters. And that's a far more practical approach that is, able to be applied within the African continent. Here we can see on the right top again how it would look like if one has to apply the angle method down to the side, and we've applied the rolling sphere method in between terminals. Earlier on, I stated that we have to be cognizant of the costs. So what we look at when we are dealing with lightning protection systems in such areas is that we want to find natural elements, so naturally conductive elements. Here's an example of a soccer field with a small pavilion. The pavilion is made up of a steel roof, like an IBR sheeted roof. We have steel I-beams coming down, and maybe even it's either concrete or it's steel here where the surface is where people are sitting. Looking at the same structure, let's apply what we've just learned. Air termination means we have to intercept this, right? So we read from the standard and says that the use of natural terminals is highly recommended, right? Because it is obviously giving us a more economic and even many times a more aesthetic solution, right? However, it says, let's use this. It even recommends us, but we've just got to ensure one thing, and that is the thickness of the natural air terminals has to be a certain value. And here we see the standard guides us again. Let's take, for instance, as I gave the example, steel galvanized as an example. In thickness A, so column A, we have 4 millimeters, which is really thick. And in thickness B, we have 0.5 millimeters, standard type of sheet. The differences between A and B is that if you are not worried about lightning puncturing, so remember I stated earlier, lightning has 3 characteristics, and one of those was the specific energy, right? The heat being exerted by the lightning current itself when it's intercepted. So if you want to handle that heat, not cause a hot spot or a puncturing of the roof or of a system, you have to have a very thick material, 4 millimeters at least. If you do not care about puncturing, like here on a pavilion, we don't care if a small hole is punctured on the roof, it's not going to cause any damages, then we can live with a 0.5 millimeter thick sheeted roof. And that is something that's quite easily accessible in African countries. One can get that even at the hardware stores. We've used this even on many of the school protection projects. So again, looking at natural elements. So moving on, we have now learned how to catch the lightning, so intercept it via the air termination system. Now we have to safely and controllably conduct the lightning currents down to Earth. Now, I use this because I believe it's the best way to remember this by. I think everyone has heard the expression sometimes in business that less is more. And in down conductors, it's exactly the opposite. So in down conductor systems, you want to have as many paths as possible from the roof all the way down to the Earth itself. And the reason for this is just to ensure that the current that you've intercepted is divided into so many paths. It does so many good things for you. It's bringing down the magnetic influence. It's bringing down the mechanical force. You know, it's just a good concept to share the current as many times as possible. So when we look at the IEC standard, and it gives us some 3 key things to consider. 1, several parallel current paths. So it indicates to us that at the very least more than 1 down conductor, right? So we should have several. It tells us to keep the lengths to a very minimum and I'll explain that in the example. And it says to us that when this down conductor passes anything conductive on its way down to Earth, that we should ensure bonding. So the equalization of potentials via a direct bond has to be practiced all the way down from the top to the bottom. Here we see on the table right bottom the lightning protection levels again, 1 to 4. And the standard gives us an average spacing which should be considered, or at least one has to try and obtain these average spacings between down conductors all along the perimeter of the building. It's definitely not always possible to get to that 10 value. Sometimes we are sitting with 12 or with 9, but the concept is such that we want to ensure multiple paths at a certain average spacing across the building. Here we see the use of two different types of down conductors. On the top right, we see a purposefully built and installed, right? So there's an external down conductor running down the side of the building. And here we see a reinforced concrete column, which has multiple steel paths going from the top to the bottom. So here we start seeing again the introduction of natural elements, such as reinforced concrete columns or I-beam steel columns coming down. And we read again from the standard that the installation of as many down conductors as possible at equal spacing, right, reduces the probability of dangerous sparking and facilitates the internal installation protections in part 4, surge protection, which Professor Gomez will cover later. It states here that the condition is fulfilled when the metal framework of structures or the reinforced concrete of these structures are electrically continuous, meaning if we want to use the reinforced concrete, if we want to use the I-beams or any sheet that even goes down, like the IBR sheeted warehouses nowadays, we see the roof and the walls are all made up of the sheet that is conductive. It says it's a great concept, use it. Just ensure that there is continuity from the roof all the way down to the earth. Obviously, because we want to conduct the currents down to the earth sink system itself. And there we state that the requirement of that is at least a 0.2 ohm value, which I think everyone knows that when you do a bonding test, at least one wants to achieve 0.2 ohms to ensure that there is a physical connection. We had the words given to us earlier that a down conductor system should safely and controllably, right, bring the currents down to earth. Now, controllably, we have the little guide that said to us, keep it as short as possible. If you have a building that has, for example, here comes a piece out and then, the atrium goes inside and it makes the weirdest, most wonderful architectural, puzzle piece. That's great for an architect, but lightning's not going to follow, this architectural outside of the building. Try and keep these down conductors as straight as possible from the roof all the way down to earth. Really get down to earth. But safely means, as you can see with this little person, one could touch these conductive elements, right? During a lightning strike, one could be touching the building, or one could be touching the dedicated down conductor, or in the example of the pavilion, one could be leaning towards the back against this pavilion during rainy times because you're hiding under the pavilion, and there you are touching a surface. So we need to ensure that we understand that human beings, the occupants, have to be kept safe as well during lightning conditions. So we need to think about this touch potential, this touching hazard that we have, and also the second man showing us that there is also a step potential, so a hazard between his feet such that the potentials are not the same and that lightning current will flow through this human being. Here in this case, the lightning currents will go through the arm down to earth where the foot of this human being is. And this is where step and touch potential hazards are introduced. So we see it, we think about it, now we have to find ways to mitigate it. Continuing on with down conductors, because it's obviously the touch potential hazard. In certain conditions, the vicinity, so where the down conductor is placed, it may be hazardous to life. That is true. I give you a very simple example. In Africa, we have many lodges, touristic places where we see these freestanding masts, right? And so often we find that they are placed in a walkway, or they are placed by the playgrounds, or something to this effect, where people will normally be. And that's an extremely dangerous thing, because here we see from the standard, it says that the hazard is reduced, right? So there could be a hazard, but this hazard is reduced if under normal operation, no persons are within 3 meters from this down conductor. And so that gives us a clue. It does not make sense to place down conductors in walkways or in a playground, because under normal circumstances, they would be people. A second item says that if we have at least 10 down conductors, 10 different ones, parallel path, remember, from the top to the bottom, we are reducing the hazard to the human being. Again, just preaching that less is not more, more is more. We need to try and have as many down conductors as possible. And remember again, if we have the sheets or the I-beams or the reinforced concrete, we obviously have tens to the hundreds of down conductors going from the roof to the earth. And finally, the contact resistance of the surface layer within the 3 meter vicinity of the down conductors is above 100 kilo ohms. So that is saying, here where this human being is standing, we need to try and ensure that he's almost not connected to earth. That's the idea, so that there could not be a potential difference. Thank you, Gopa. If none of these conditions on top are fulfilled, we need to adopt the following possible protection measures. Number one, we have to insulate the exposed down conductors with at least a 3 millimeter thick polyethylene type of conduit. So here I show you the example again. The first was we either lift this human almost into the air with the contact resistance. It's quite often seen inside substations where these stones are used, this crusher stone, because that increases the contact resistance. But otherwise, we have to insulate this down conductor. And a very simple and pragmatic way is to use a conduit that's made out of PVC that's at least 3 millimeters thick, right? And place the down conductor inside this so that a human being cannot touch the conductor itself. We have to ensure, or we could use equipotentialization, right, between the earth termination system. So really here, build an earthing system underneath this human's feet or under that human's feet such that there would be no potential difference. Or finally, we have to use physical restrictions, so almost barrier off an area, or place warning notices that people should not be in this vicinity during a lightning strike, or at least lightning conditions. But a designer needs to think of these things, because a warning notice or a physical restriction at a what is it called, the pavilion next to the soccer field, this is never going to work. People are going to shelter below this building, right? People are going to go there naturally. So one has to think of the other methods, that is available to us in order to protect. So this is where really a designer needs to think of each and every case when we are doing our lightning protection mitigation. Okay. Moving on to the final part, the earth termination system. Most laymen have heard, the term, the path of least resistance. And I obviously conduct a lot of seminars, and I've heard quite interesting definitions or understandings of this word. But in essence, the concept was derived from how we all learned of electricity. And we learned of electricity really in a low frequency 50, 60 hertz type of domain, and there the concept is quite well understood. However, when we're dealing with lightning currents, which is, a mega giga type hertz, it's a very high frequency current, the path of least resistance becomes almost the second or the third item. Here we read from the standard says that the shape and the dimensions of the earthing system are the key factors. It says that it's important, so we strive towards a low resistance, path of low resistance, the 10 ohm value we also know, but it's not the critical items. The critical items under high frequency behavior for the earthing system is how we have shaped it, so where it is lying, and the dimensions, so the size of the conductors itself. The standards gives us two type of arrangements. The first is type A, which is where we are using for simple structures, maybe a simple home as an example, or a small telecommunication tower. It is where we have either a single vertically driven into the ground electrode, or we have a trench that we have made and we have a single horizontal conductor. Type B arrangements are a little bit more for higher risk areas, for larger buildings like school buildings, etc. This is where we have a completely integrated system. I think the most common words used are things like earth mats or earth ring. This is where we are placing the type B arrangements, so known as an earth electrode or an earth mat. The type A, we can see here on the top right, we have a single vertical electrode or possibly a single horizontal electrode. The standard guides us, remember we said dimensions and the shape matters, that we need to ensure if we use a horizontal electrode that we at least keep a minimum length, and the minimum length is 5 meters. If we do a vertical or even an inclined electrode, so inclined meaning at an angle, we have to have half of that length. So this vertical electrode needs to at least be 2.5 meters deep, right? And notice also that the standard guides us that this 2.5 or even this 5 meter always has to start at least a half a meter below the contact surface, so the above ground portion. And that's very important because that's part of the earthing system's assistance in order to ensure that you are safe as the human being. For the type B system, here we can see it's a ring earth electrode or an electrode around the entire building. Right there we can see it. There we use the mean radius examples. So we work out the mean radius of the square, and that value still has to be greater than the minimum length. And here we see the figure from the standard. It states that, as an example, for lightning protection level 1, if the soil resistivity is 1,000 ohm meters, that we need to have a length of 20. So soil resistivity is a value not so commonly obtained because we don't have the instruments or we don't have the skill level in country. So there are also in the table quite an interesting way to go about this, and here it is given in the table to say if you don't know or cannot measure the soil resistivity, look at this. If you are in a marshland, very wet, very humid environment, you're going to expect very low soil resistivity values, 30 to 100 ohms. If you are in clay, very clay conditions, you're at 150 ohm meters as an average value. Moving on towards maybe gravel, normal agricultural soils and sand where we have our maize planted, we're looking at about 1,000 ohm meters. And if we are in rocky, stony type soil, we have a very high ohm meters. And so this is at least an indication. If you look at your surroundings, let's say you're in an agricultural gravel type normal area, you're at 1,000 ohm meters. We can use the table at 1,000 ohms and we see 20 meters is the length. So if we had the horizontal, that would have to be 20 meters. and the vertical would have to be half of 20, so that would have to be 10 meters deep. Right. Again, just giving you some practical approach compared to if you cannot deploy the Venner method, where we are measuring to, you know, a comma spacing the actual soil resistivity. What is important on type B systems, which I failed to mention, is that if you are using ring earth electrodes, that at least 80% of the ring itself, so of the conductive part you're using, either steel or copper, whatever it might be, has to touch earth itself. It has to touch the soil. Otherwise, obviously, it's not doing the part of dispersing or distributing the currents to earth itself. Right. The material requirements, remember we said that the earthing system, one is the length, the shape, and the other one is the dimensions. So here we have a table that's given to us where we have summarized all three parts already. Air termination, the catching part, down conductors, the conducting safely and controllably part, and earth termination, the dispersing it whilst minimizing dangerous conditions. If we use copper material of solid configuration, we see that we need a 50 mil squared thickness for air terminals and down conductors, and the same for earth termination systems. If we are using aluminium as a stranded material, 50 mil squared for air terminals and down conductors, but we are not allowed to use it as an earthing system because aluminium gets corroded very quickly, and you would have to replace that earthing system very frequently. Steel, galvanized steel as an example, when we use solid, we need a 50 mil squared air terminal, and for the earth termination, at least a 78 mil squared. And so these are simple tables, so we know now the length we would require, and we then have to only ensure that we reach a certain thickness in terms of the components used for air terminals, down conductors, and for the earthing system. Although the IEC speaks very clearly of using compliant components, so compliant components is components that are tested towards the 62561 series, part 1 to 8. We find that it's quite often very difficult to source compliant products in certain countries. So what we would then advise is that one takes the local products and compare at least the dimensions of this product with the compliant products, or at least try and find a distributor of the compliant products and see if you cannot find a way to import these products to your country. Right. Final slide is the external side has been dealt with. Now the internal lightning protection system. And I know sometimes it seems like a biology lesson almost, this picture from the standard. I can promise you in the new 62305 standard, I've actually personally given a new drawing so that we can sort this biology sketch out, but at least it serves its purpose. And I explain the drawing on the right after reading to you on the left-hand side from Wikipedia. The practice of intentionally electrically connecting all exposed metals, right? Not designed to carry electricity in a room or in a building, right? As protection from electric shock. If a failure of electrical insulation occurs, all bonded metal objects in the room will have substantially the same electrical potential. So it doesn't matter if it goes high up even into the kilo or megavolts, they will all have the same because they're all connected together intentionally. So that an occupant of the room cannot touch two objects with significantly different potentials. So we are avoiding shock. Even if the connection to a distant earth ground is lost, the occupant will be protected from dangerous potential differences. And if there's anything you would ever remember about internal lightning protection system, and it's exactly this. It doesn't matter about the earthing necessarily. It doesn't matter about how the lightning protection system function on the outside. Internally, if we ensure that all metals which I can touch as a human being, so the standard speaks of within an arm's reach, is connected together intentionally, we are avoiding a shock or an electrocution because we have ensured that the potentials are at the same value. And this is what we see with the drawing on the right. If we have a water pipe and we are crossing into the internal side of a building, so this light gray is the outer walls of a building, the water pipe goes in right where it goes in, where it now can be touched. We have to bond that incoming service either directly or via a suitable surge protection device. Surge protection devices are used, for example, the power line. If the power line comes from outside, enters the building, so at the boundary wall, we would insert a surge protection device to ensure equipotential bonding. And this is best explained by the graph on the right here, that in a house you would have a main earth bar. You might have the external lightning protection system all being interconnected via, in this case, the type B earthing system. Goes back electrically to the earth bar, and you would connect the earth cables to the earth bar. You would connect the shields of telecommunication cables to the earth bar, but you could not physically connect the live wires of your power system or the transmit and receive wires of your telecommunication system to earth. And this is where we are using suitable surge protection devices, because during the condition where there is a huge potential exerted onto the earth bar, when we need to ensure that these potentials are equal such that we don't have damages, this is when the surge protection devices switches on and creates an equal potential, then via bonding, right, such that the equipment connected to the power line or the telecommunication lines are not damaged. And that is something I so often see, is that people are not understanding that the surge protection devices as a first principle or first measure is actually there to ensure lightning equipotential bonding between live parts and the earthing system itself. Yes, Gopal.
Mr. Alexis, yes, we have passed the time, 5 minutes extra. So our next presentation is on SPD, but so I request you to make it as quick as possible.
We are done, so thank you, Gopal. The last part is that we have to do direct bonding. So the surge protection is the indirect. Direct bonding looks like this, where we are ensuring bonding from cable trays to the down conductor or earthing system, bonding of rail lines which we can touch, railways. We have also here the earth bar which we showed earlier, and a very simple understanding as to the sizes are given again. If you are bonding between earthing terminals, earthing bars, we have to have at least a 16 mil squared. If we're only bonding internal metal parts like here, then we need at least a 6 mil squared, so a lesser rating. And that's it. I can stop with the surge protection side because my dear friend Chandima will cover that, and we will not have time today to talk about the testing and inspections. But basically ending, we will say that an effective and safe lightning system does not mean it has to be expensive and or complicated. I thank you for the time today. I ask that if you want to learn more or even learn about multiple other subjects, we have launched the Lightning Protection College online. Here's the website. You can please join us and learn about lightning protection, surge protection, and multiple other modules. Thank you very much.
Yes, thank you very much, Mr. Alexis. Now we go to the next part of the presentation. The next part is about protection of the surge protective devices for low voltage system. And the presentation is by Professor Chandima Gomes. Professor Chandima Gomes is the professor in the high voltage engineering at the University of Witwatersrand and at South Africa. He's a member in the TC 81 of IEC committee, Technical Committee 81, which is responsible for the preparation of IEC standards 62305. He is a member in the Mirror Committee, which is the South African committee. I would request Professor Chandima, please, you can start your session on the internal protection or search protection devices. After that, we go back to Ms. Foster. I hope you received the presentation of Ms. Foster.
Thank you very much, Mr. Gopakumar.
Can you hear me? Chandma, can you hear me?
Yes,
I'm in.
we can hear you.
Okay.
Yeah, Foster.
Yes, I'm in.
Yes, Foster, what we can do is that after my presentation, you can take up yours.
Yes.
On the other hand, would you like to take it up now?
I think whatever is best for you. I can take it up now.
Sure, no problem. I'm quite okay. GK, is it okay?
Yeah, that's okay.
Great.
Okay.
Please go ahead, Foster.
So let me share. I can share?
Yes, please.
Okay. What's happening again? Oh, no. Okay, I'm sharing. It's still loading. Okay.
Yeah, we can see your slides, but you have to put it on the full screen.
Okay. Slowed. Oh dear. Okay. Are we okay now?
Yes. Let me invite Dr. Chandima for the next presentation on surge protection devices for power lines. Dr. Chandima, please, please start your session.
Thank you very much. And good evening or good day to all of you. And just to give you an idea of what I'm presenting today, it's about lightning protection of low voltage systems. In one of the previous presentations under Solnet, run by Dr. Sriram, I conducted a presentation on lightning protection of high voltage systems and medium voltage systems. So here I'm focusing only on the low voltage systems, and also I'm not going to ELV or the signal system protection rather than just one small slide. And also, please understand that this is the first presentation and it is just 40 minutes. So I'm touching very shallowly this subject without going into the details and also into the specific cases, so that if you want some to get enlightened on anything deeper, please you can ask any questions, and also we can go into further presentations in the future. Okay. And so all of you know this, I'm sure even Alexis, my friend, has told you about it. When it comes to lightning protection, we basically divide it into two parts: the building protection, which Alexis covered, and the other thing is any transient which is coming through the service lines we have to deal with, or coming from the earthing system, and it is called the surge protection. And today my topic will be around this surge protection. Okay, when we are doing any scientific or engineering practice, we have to follow some internationally agreed method, and in lightning, we have IEC standards, which is prepared by the IEC TC81 committee. And today I'm happy to tell you that there are 3 members of IEC TC81 International Committee here, myself, Mr. Alexis, and Mr. Gopakumar, so that if you want to know about the IEC TC81 committee base, the most recent developments, then you can ask your questions, because we are having a series of meetings during the last few months, and most probably the next revision of this the standards will be out from 2021 until 2023. They're supposed to be out by 2018, but due to various reasons, they were shifted towards future. And you will find the parts 1, 2, 3, and 4 separately coming out in the next couple of years, as soon as they have been approved from the committee. And today my presentation is based on IEC 6.54, which is on the electrical and electronic system protection. And also that is within the structure, that's very important. But in the modern days, rather than protecting inside buildings, people are more concerned about protecting these basically outdoor systems like telecom, wind, railway, solar, defense, airport, naval, and so on. But today, within 40 minutes, I'm not able to go into that. So I'm sorry. These specific systems are not being covered in today's presentation. Okay, if I go very quickly on the causes of transients, lightning is a very basic transient currents into your system. It may be direct strikes or even distance lightning. But there are some other cases as well, like arcing of grids, grid failures, and so on. Then brownouts, blackouts, grid switching, other operations like adding or removing loads. In all these cases, you may get transients. So it is not only a phenomenon related to lightning. Lightning is a very predominant cause of transients, but there are many others as well. And not only from external means, even internal environment can generate transients. Whenever you are switching electrical motors, air cons, any inductive load, you can get transients. And also something that I have not mentioned here, and during the last couple of years, I have done a lot of research in that area. Whenever you are switching on and off, actually energizing and de-energizing, if I say in the very correct terms, because it happens automatically, the power factor correction capacitor banks, especially if you have centralized power factor correction capacitor banks, their energizing and de-energizing processes can create some sort of transients of ringing nature, which can be harmful to your equipment. And most often, all these transients are covered under lightning protection, because when you give solutions to lightning protection, most of these transients are also being covered, except for few, like the transients generated by power factor correction capacitor banks. They can bypass the SPDs. Now, how can lightning can cause damage? There are basically 2 ways. One is if a lightning strikes a power line, either the line or the neutral, basically the line, then a large current may pass through your equipment. We call it a differential mode transient because now you have a potential difference between your line and neutral. And most often that causes overcurrent heating, and you see melted parts in your equipment when you have differential mode transients. And also if there is a nearby lightning, most often as the power lines and the neutral wire are quite closer compared to the distance from those lines to the lightning strike, you get almost the same voltage induced in the line and neutral, so that there will be a potential difference between your line or neutral and the earth, so that you may get arcing from your line to the earth, which is most often causing dielectric damage. And in these cases, you may see burn marks, which you usually don't see in the case of differential mode transients. Okay, now let's see that if you take a TT wiring system, I'm not going into the details of wiring systems, and I'm sorry for my African colleagues, because in Africa, most often in many countries, the wiring system practiced is TNCS, where there is no the fault currents usually flow along the neutral itself to the transformer, but at the utility you have a neutral and earth separately. But I'm just using the TT wiring system, but you will understand this phenomenon. This is mostly practiced in South Asian countries, where there is a utility earth and there is no connection between the neutral earth at the transformer and the utility earth at your premises. Now imagine that if lightning strikes a line, then what are the paths, the possible paths? One is that the current will flow through the transformer. And don't forget that in this case, the transformer is having a very high impedance due to the coiling. And therefore, most often the current will flow in the form of an internal arc inside the transformer between the coils. Or there is another way, you can have an arcing at the wire, the line itself, from the line to the neutral, and the current may flow through the star neutral point at the transformer. And also, this is what happens most often when lightning strike close to your building. Quite a high part of the lightning current may come into your premises, and basically at a distribution board or the main panel, or even inside an equipment, the current may flow from usually at basically at inside an equipment, the current may flow from line to neutral and flow into the ground. So this will give rise to a basically to a differential mode transient damage. And there is a chance that there may be an arcing inside power panel, main panel, or distribution board, sub panel, an arc happening from line to neutral. And this is the other way. This is very common in countries where TT wiring system is practiced, especially if the transformer which is feeding your building is having a quite a high earth resistance at the star neutral point, and if your building is having quite a low earth resistance, usually we say that your earthing system should be quite low, but this is one of the negative side of that as well. there may be an arcing from line to earth. Usually happens inside the main panel where the main panel get blasted, or it can happen inside an equipment, in which case your equipment will definitely be experiencing a catastrophic failure. Okay, so in most of these cases where you see a red color circle or ellipse, there is an arcing. The blue color ellipse show you a melting. There's another way of having a lightning damage. Say for an example, if you get a lightning very close to the transformer earthing, or imagine that lightning current hits the medium volt side of the transformer, and the lightning current pass into the earth through the surge protectors, and then the area around will have a high potential rise, especially if the earthing system is not that good. And then you're having low potential at the other side at the building, so the current will flow like that, and there will be again an arcing, usually at the main panel, sub panel, or at an equipment in the building. And the same thing can happen in this way as well. Okay, and what is the principle of power protection? It's very simple, apparently very simple. If you use a surge protective device, which is used to protect your equipment and systems from lightning or any other transients, it is connected in parallel between line and neutral and earth. But I will, for the simplicity, I will show only one SPD. Usually there are two SPDs. Now, under normal conditions, an ideal SPD, ideal means something not in this world. It is perfect. It remains open circuit, and only during the transient, it will become closed circuit, so that the transient will pass into the ground, and during the period of the transient, your load is detached. In an ideal case, detached from the power supply for few microseconds, and then it will come back again. So this is the ideal situation. But in reality, an SPD goes not from open circuit to short circuit, which is the ideal situation, but from a very high impedance to a very low impedance situation, when the potential difference between the two sides of the SPD goes over a certain critical value, a threshold value, which we call the voltage protection level. Rather misleading term. I'm not going to discuss about that here, but some people take it in a quite an opposite manner when they're describing what happens. The voltage protection level is at which the SPD will start operating. So actually, until the voltage protection level, the transient voltage is seen by the load. That means the load will be encountered, or load will be exposed to the transient voltage until it reaches the voltage protection level. So this is what will happen if a lightning hits a transmission line, distribution line, and then it will come towards your load. Actually, what happened, this is in the ideal case, we say that when it comes to the SPD will go from low potential, the high impedance mode, to low impedance mode, so that the current will pass into the neutral side, and a part of the current will go to the substation earth, and then this current flow into the substation earth increases the potential at the at one end of SPD S2, and then it will operate, send in the current into earth. Okay, so this is basically the simplest way of presenting how an SPD works. But now in a three-phase system, you can connect SPDs in two ways, connection type 1 and connection type 2. Both are accepted in the IEC standards 623.054. I will show you the mechanism of connection type 1 only to save time. Now imagine that if lightning strike line 2, then its potential goes up so that SPD goes into low impedance mode. Now the neutral is in one potential, so that all the other SPDs are now subjected to difference in potential. So they will operate and the whole system becomes single potential. So there will be no potential difference. And the other operation of an SPD is that imagine that your earth potential goes up due to a nearby lightning. Now the S1 will go into low impedance mode, and then S2, S3 and S4 goes into low impedance mode. Now your whole system is at high voltage. Say for an example, if the voltage at the earthing system goes to about say 8 or 9 kilovolts or 10 kilovolts, all your L3, L2, L1, N and E are nearly 10 kilovolts, so that there will be no potential difference inside your equipment, although the whole potential has rise to a high value, so there will be no damage. Okay, now I'm going to the little realistic way of presenting what I told you. Now consider that a lightning current enters into a load. What will happen? That current, when it passes through the load, you will get the depending on the load resistance or load impedance, you will get a voltage drop across the load. And according to my example, say that the voltage goes to up about 5 kilovolts. Now consider a load which can withstand an impulse voltage up to about 2 kV. This value we call the impulse withstanding voltage of the load. Usually when you're buying a load, these specifications are there if that equipment is according to proper standards. And definitely in this case the load will be damaged because it can withstand only 2 kV and the voltage goes to 5 kV. So what we do now is that we connect an SPD, and now what really happens is that, say for an example, we take an SPD where UP value is 1.8 kV. That means the surge protective device will give out only 1.8 kV. So if it is the case, then my equipment is protected because it can withstand up to 2 kV. What comes out of the surge protective device is 1.8 kV. Let's see what happens now. Okay, so the current comes. And this is what happens at the load side. You can have a look at the curve at the down. If there is no SPD, this is the voltage waveform you will get. With the SPD, this is what you get. So this is the UP value, and this is the type of behavior you will find if your SPD is made of metal oxide varistors or xenodiodes. And the same SPD, if it is made up of spark gap or GDT, gas discharge tubes, and then you will see a behavior like this. Again, this is UP. Okay, hope that you understand. Now you will clearly understand that the equipment will always see a minimum voltage, minimum transient voltage of UP. In reality, this is more than that. So now the thing is that, okay, in order to protect your equipment, you are going to select SPDs for a power system. Now you have to consider, if you are an electrical engineer who's going to give lightning protection to a building against transients that coming through the service lines, you have to consider several parameters and several factors. What are they? Where to install? Transient current handling capacity, voltage protection level, OLED and let-through voltage. I will explain you those things later. Response time, which is not that important when you consider UP value. Maximum continuous operating voltage and temporary over voltage. These are the basic factors you have to consider. Then if you are going to protect signal lines, communication lines, data lines, and so on, you have to consider, apart from the previous parameters, in addition to that, you have to consider system operating current and voltage, because most often your SPD has a component which is in series with your line, whereas in the power SPDs, most often you have only parallel components between line and neutral. So as in the signal lines, you have a series components, you have to consider several other things as well, like the operating current and voltage, then bandwidth and insertion loss. Definitely there will be an insertion loss because there is a series component, but you have to consider whether it is bearable for the system, the number of pins, cable type, plug type, and so on. Mr. Gopakumar, one small thing, I can't see the time, so please remind me 5 minutes before my scheduled time, okay?
Sure. We have 15 minutes more.
Great. And then, if it is an ideal SPD, what we can expect is, ideal means something out of this world. It will be able to handle very large current, say that it can withstand 100 kiloamperes. And after withstanding 100 kiloamperes, it should give very low UP, like 0.6 kV. If we have such a SPD, it's wonderful. But unfortunately, the current handling capacity and UP values of an SPD are directly correlated. What does that mean? When the current handling capacity increases, the UP value will naturally increase. So that, for an example, if you select a peak transient current 3 kiloamperes in an SPD, its UP value may be 0.7 kV. But on the other hand, if you select a 50 kiloampere SPD, its UP value may be like 2.8 kV. Okay, there's a typing mistake there, 2.8 kilovolts. Now, because of that, when you are selecting SPDs, we have to consider that first factor I told you, where to connect. So if there is a building, then you have to connect these SPDs at various places with varying specifications. So closest to the load, we call it zone 3, it may be zone 4, 5 and so on as well, but usually in most of the cases it is zone 3. These are the plug point level where you get the power to feed your equipment. Then zone 2, usually the sub panels. Then zone 1, which is the main panel where the wires are coming, the power supply is coming from outside. And the zone 3 will get the lowest I and lowest UP, and zone 1 should have the highest I and highest UP, and zone 2 is in between that. So lightning protection zonal concept, if I put you the same thing I discussed with you, if I put it into a diagrammatic form, this is what we get. We call zone 0A what is not protected by even your structural protection system. Then zone 0B what is protected from your structural protection system. Then LPZ1 is the place where you just enter into the building. Z2 and Z3, the same thing in a different way, in a pictorial way. And the SPDs you are selecting for zone 1, they should be tested for class 1, and they are referred as in the IEC standards as type 1 SPDs. Now German products are also, most of the products for South Asia, Africa and so on are coming from Germany, now coming from other countries as well. They have the German standards VDE 085, which is now suppressed. It is superseded by the IEC standards which German adopted. But according to the previous German standards, they are classified as type B, C, and D, which is classified as type 1, 2, and 3 in the IEC standards. But still, I have seen some German products still adhere to this BCD nomenclature. So that's why I'm still keeping this last column for your reference. And also you may find SPDs marked as type 1 to 2 or 2 to 3. That means it can handle currents which type 1 SPD can handle, and it will give UP values which SPD type 2 will give. So these are improved ones, and type 2 and 3 as well. And now there are some patented products which are type 1 to 3. So this is still not in the market, and they are very much applicable in space restricted sites like BTS, the base transmission station in tower sites, and various other places where you can't find zonal classification or enough distance to classify the building into zones. And also in mobile vehicles like outdoor broadcasting vehicles, these type 1 to 3 SPDs are very advantageous. Okay, then transient current handling capacity. We have 3 types: impulse current, Imax, maximum current, and rated current. What is impulse current? This is a test specified for zone 1 protectors, which is tested for a current which is named as 10 microsecond by 350 microsecond. We call it 10 by 350 waveform. And when that waveform is applied, this is a generator, what you see in the picture below, 10 by 350 current, impulse current generator. When you apply this current into the SPD, what is the maximum current that SPD can withstand? This is the capacity or the specification of this current. And now I'm giving you some idea, especially for the tropics. We are coming to a little strategic point now. IEC specify IIMP of 12.5 kiloamperes. But for the last 20 years as a consultant, I have been working in many Southeast Asian countries and African countries as well, especially in the tropics where the lightning density is quite high. What we have seen is that we may need SPDs which are having higher current handling capacity than what is specified by IEC. There are arguments, there are debates, okay? So therefore, that's why I term this as consultant's choice. So this is what usually we specify. And then the IMAX class 2 test, this should be tested for the SPDs recommended for zone 2 and zone 3. And this is a 8 by 20 microsecond current waveform generator. And this is again, I'm giving you the consultant's choice through my life experience. And I'm also stating below what is the IEC specification. And then the rated current. Every SPD should not only be tested for the IIMP or IMAX. Apart from that, you have to apply 8 by 20 microsecond waveform 20 times and say what is the maximum current that the SPD can withstand. This shows how robust the SPD for multiple lightning currents. Again, there's a rule of thumb of rated current should be greater than about 1/3 the IMAX. And then we go to voltage protection level. So as you are now quite familiar with this is the maximum voltage that the SPDs alone will give out. But in reality, this value will be greater than the UP value, the voltage which is seen by the load is greater than the UP value because of the voltage that is generated along the wires, the connecting wires. So altogether, the voltage across the wires and that of UPs called the LTV or lead through voltage. And so let me quickly show you what this means. So the total voltage will be V1, V2 plus V3 plus V4, where V1 and V2 are the UP values of the SPDs. So finally, what we see is these type of voltage differences between line and earth, neutral and earth, and line and neutral. So your equipment impulse withstanding voltage should be covered by this, should be more than these voltages. Okay. So in order to minimize the lead through voltage, you should have as small cables as possible, usually 50 centimeter. Actually, now the new standards are giving another equation for that. I'm not going to that due to the time restriction. Better stick to 50 centimeter maximum length between line and the SPD and earth. So these are some values of impulse withstanding voltages. These are some standards which gives impulse withstanding voltage of equipment. Then the class 3 test, which we call the combined generator test. This is usually all class 3 SPDs, type 3 SPDs should be tested for this class 3 test. Apart from that, class 2, the type 2 and type 1 SPDs are also tested for that. But it is compulsory for type 3 SPDs, where you apply a current and voltage waveform generated by the same generator, which we call the combi generator or combinational waveform generator. Then for the type 3 SPDs, when you apply a voltage of 6 kV and current of 3 kiloamperes, what you see is the wave shape at 1.250 and 8 by 20, then the output voltage should be 0.6 kV. Then for all other SPDs also you can test it, but make sure that when a manufacturer says that my 50 kiloampere IMP or IMAX SPD has 0.7 or 0.8 kV UP value, this is very, very impractical. And most often what they may be telling is that their nominal current handling capacity is 50 kiloamperes, but they have tested it for the 6 kV 3 kiloampere waveform, but they try to imply that when 50 kiloamperes is applied, the output voltage is 0.7 or 0.8 kV, which is not feasible. This is a combinational waveform generator. I'm going a little faster. And then maximum continuous operating voltage, which is a very important parameter. Actually, it gives you, in the case of there is a sustained over voltage, what is the maximum value that the SPD can withstand? Now, under nominal frequency, if there is a sustained over voltage. Now, for an example, for SPDs like UP equals 1.8 kV, the MCOV may be like 300 volts or less. What IEC says is that for a TT wiring system, for an example, the MCOV should be at least 1.1 U0. That means 110% more than the nominal RMS voltage. But what we have seen in many countries where the power quality is bad, such values, for an example, for 230 volt, then it's about 255 volts, the MCOV, according to IC standards. But if the power quality in your country is not good, then the SPD may be damaged when you select a low MCOV value. So that you better go for a little higher MCOV, but this is very subjective, okay? It depends on the country. Always you better go for, low MCOV values as much as possible, but at the same time they can withstand the power quality. Because when the MCOV increases, naturally the UP value of the SPD will also increase. Therefore, you can't go for very high values of MCOV if you want lower values of UP. And then response time, I'm just skipping because response time is not that important nowadays. If you select your UP, then response time does not mean much. And then maybe this is my last slide, or one before last, neutral shift problem. We have another problem when it comes to the SPDs. Now imagine we have a system like that where the line 1 is now switched on. So that means the load which is connected to line 1 is being operated. So if while it is being operated, so L1 is feeding the load, there will be a neutral break. Say somebody cut the neutral or a tree falls into the neutral, then we say that the neutral is broken. Now what happens? There will be no current flow in the line L1. Therefore, the whole voltage in the line L1 will be the same. So in other words, V4, earlier the neutral voltage, now goes to V1. Now you will see that voltage across SPD, S2 and S3 becomes line to line voltage, so that your SPDs now are exposed to line to line voltage rather than line to neutral voltage. So that will most probably damage your SPDs unless this is we call the temporary over voltage, unless your SPD has a TOV which is able to withstand for quite a long time this type of a line to line voltage. Now this is my last slide actually. When you're connecting SPDs, this is the way you connect the in, out and the earthing wire. And I'm sorry that I have no time to explain you why they are connected in this way, why the inward wires are perpendicular to outward wires, and why the earthing wire is separated by some distance. These things shall we cover on another time. Thank you very much for your patience.
Thank you very much, Chandima, for the nice presentation. We have a few questions, not few, actually we have only one question, which is to Professor Chandima. Can you explain briefly about I-impulse and I-max again? The question from Anuradha Lianage, I think from Sri Lanka.
Okay. I-max, I-imp is the current which is which should be used to test the SPDs which are connected at zone 1. The zone 1 SPDs, that means the SPDs you connect at the main panel, are subjected to most often direct current coming from outside, so that they have sometimes impulse current, the impulse component, plus a continuing current, which I didn't show you. Usually it comes under the characteristics of lightning. The impulse part plus the continuing part together contains a rather large energy content, so that the SPDs at main panel may expose to this large energy which comes with the transient. Therefore, we have to make sure that the SPDs at the main panel, zone 1, can withstand such energy content. That's why we test the zone 1 protectors for this I-imp, which is given by 10 by 350 microsecond waveform. That means it has a rise time of 10 microsecond and half peak width of 350 microseconds. So that if you integrate the I squared with time, I squared dt integration, which we call the action integral, you're getting rather large value. That multiplied by the impedance of the SPD will give you the energy dissipation inside the SPD. When it comes to the other SPDs, like zone 2 and zone 3 SPDs, they will be subjected most often to the impulse part of the current, so that the impulse part has a large voltage, very fast rise time. However, the energy content is not that high. So you will see that when you take 8 by 20 microsecond waveform, it has more or less the same rise time. One is 10, one is 8 as the I-imp, but the width of the waveform is now much less. In the previous case, the half peak width is 350 microsecond. In this case, it is 20 microsecond. So all your type 2 and type 3 SPDs, you have to test for the class 2 test, which is I-max. Hope that you understood. If you have any further questions, please you can raise.
Yes, thank you very much for the detailed answer. Now I request the participants, if you have any questions, you can unmute and you can ask the questions. Please come forward and utilize the opportunity. I think if there are no questions, then probably we can end up the program.
Thank you very much. And I think if Foster is around, you can give the thanking speech. Before that, let me introduce, not introduce, actually give a detail about the speakers today. Actually, Mr. Gopakumar gave the introduction to all of us, but nobody gave Mr. Gopakumar an introduction. So actually, just to, as we have little bit of time, and then all three speakers can give their views as well. Mr. Gopakumar is one of the pioneers in lightning protection and lightning safety promotion in South Asia. We too met about 20 years ago, and since then we have conducted a large number of programs in South Asian countries. There was a time that when I was in Malaysia, I used to visit India twice a year at least, and every time, say first time, say around March, we travel about 5 destinations in southern Indian states. We conduct 2-day training programs in each state, like 2-day program in Chennai. Then after the program, we have a team of about 3-4 people. Then we take a flight or drive into another state in Karnataka or in Hyderabad and then in Vizag. So likewise, we go around southern Indian states. Then in the next half of the year, we meet again, and then again about 5 2-day programs within about 2 weeks. It's so hectic. One in Delhi, next one is in Pune, then in Calcutta. So it's a tremendously hectic program, but we enjoyed up to maximum. So, and it was all possible due to Mr. Gopakumar's untiring efforts. So I have to thank him. He's a leading engineer in lightning protection in the South Asian region. Now he's expanding to other parts of Asia as well. So I have a special thank to Mr. Gopakumar, and he's a DC81 member as well, and a member of many standard committees. So thank you very much for your untiring support for all these years. It was wonderful. I have no words to thank you. And then,
thank you, Professor Chandiba.
Yeah, then I would like to say today for the first time that I found my African Gopakumar in South Africa in Mr. Alexis Bawais. So he's a dynamic person, and I see actually, I think Alexis is much younger than both of us. I'm elder to all of you, and Alexis is the youngest member of my team, I may say, because we are a global team, not just one part of the world. And what I see is that actually Alexis is the key person who's supporting Marianne Cooper in giving protection to buildings in Uganda and in many African countries. And I think together we can do a lot. I think I talked enough. And then Foster, she's someone that we all groomed up for the last say last 10 years, and she is becoming a leading a leader, playing a leading role in Africa. So Foster, you have all the support from us, from India, from South Africa. We are with you. And with that, I will end up and I will hand over to GK. You can pass it to Alexis. I think Alexis would also like to make some comments.
Yes, over to you, Mr. Alexis. Some comments about the program?
So no comment, just really thankful that we have these sessions. Would like to ask that anyone that has such initiatives to reach out to us, Janima, that we don't always have to plan these things ourselves. Perhaps even the initiatives can come from any country or any place in the world. And with our networks, we will be able to support them with such good initiatives. So I think that would be a message from my side. Let's help spread this information and knowledge we have been given by others, such that we could give it to the next person.
Thank you very much. Over to you, Ms. Foster.
Okay, thank you so much, everybody. I'd really like to thank Mr. Kumar also. Welcome to Africa now. You will not only be in Asia, you will now be in Africa. Also, we truly appreciate that you could accept to moderate our webinar. It's really been a success because of you. I'd like to thank Professor Gomes and Alexis for agreeing to speak at this event. Thank you so much. It's just a pity, really. Maybe it's because it's the first time things just went wrong. You know, I had so many messages and WhatsApp, and people are struggling to get in. I think we may have to discuss to see how this can be improved. I will discuss with people this side to just find out how many managed. And if maybe so many didn't manage, we probably could do this again so that our people can also benefit. Because I was really, I managed to get quite a good number of Zambians to sign in. And now I can see a number of messages. Maybe this is why my phone, because I was using my phone for a hotspot. That's why my phone just went haywire. Fortunately, my husband was nearby, so I just grabbed his laptop and his phone, and that's how I managed to get back in. Because my phone and my laptop just gave up on me. So we really, I personally am really grateful because we need this information out here, not only in Zambia but in Africa. We had some Ugandans also that signed in. I registered. I don't know if they managed to sign in. I'll check them out also. Otherwise, we're really grateful. Alexis, I hope you can tell us more about the online program that you talked about, so that we can have access. We can manage to access it. And I'd like to really thank all our distinguished participants who managed to register and to sign in, because this has been a success because of all of you. So thank you so much. We hope to see you again sometime.
Thanks, Foster.
Yes, thank you. So by this, we end up the program.
Yes, sir.
I think you better make a announcement. I think many people are interested in the video, and
yes,
about how to get it.
Yeah, so we will make the video available to you, and you will get the email like the joining link which you received today. We will send you a link for the video so that you can download or you can see the video. So this will be sent maybe day after tomorrow.
That would be great. And then you remember the last webinar we had, and you did send the email and the videos, but I couldn't access the videos. I could only access the answer and question session.
Okay.
Yeah.
But the other two sessions you could access. Only the question answer session you could not access.
No,
Is this
no,
correct?
I couldn't. I couldn't
Okay.
access the videos.
All the videos.
All the videos,
Oh,
except
okay.
the question and answer sessions.
Okay,
I don't know why. Yes, please.
Okay, we will check it.
Oh, and then
So-
before we go, I think I would also love to thank Salnet. I can't skip my friend Salnet for the comradeship we've shared and the support. Thank you so much, Salnet. Thank you so much, Shama. Truly appreciate.
Yes.
Yeah,
So-
you're most welcome, Costa, and listening to you.
Thank you.
Shri, would you like to make any announcement about Solnet program? So any near future events?
I think I'll send an email in a day or two because I'm on vacation for a couple of days, so I'm
Yes.
not planning anything at the moment. So yeah, we are on this the Shera festival. So
Yes,
I'm
wish you a very happy festive season.
Yeah. So I'm in Lumini right now, so celebrating with my
great.
parents.
Where the Lord Buddha has born.
So yes, it is. So it will be very soon. We'll make some announcements regarding about them. Perhaps ADPC wants to make some sort of LPS training program in a couple of weeks. Then we have to fix the time and everything. So I'll let you all know and invite the prominent figures like Alexis, yourself, and GK, of course. Then we'll send the information around.
Yes.
Thanks, Shiram.
Yeah, GK, it's and Foster, thank you for remembering me, and it's over to you. It's of course a wonderful program, and maybe very little people are left now.
Thank you. You're welcome.
Okay.
Yeah.
Thanks for all the participants and the organizers, Ms. Foster, Mr. Alexis, and Professor Chandima. So finally, we end up the program. Thank you very much. Bye-bye.
Good night.
Thank you.
Thank you.
Bye.
Yeah.
Bye-bye.
Bye.